is this classical quantum classical correspondence is a field of my research interest, not for qubits. I'm not doing with qubits. Qubits is not my field of research, but nevertheless for some other also important systems. And you see everything in principle, everything that you have locally. So I mean at one place that you have simultaneously access to this. You can simulate classically. So what means simulate classically? This means that you can, so in quantum theory, there is some outputs, there's outputs sometimes random, yeah? So because quantum states and all the things I told you already, that probability to find a particle here or in another case, so this is random events. And you should understand that the question is either we can use classical machine and classical random generator in order to simulate it. Yes, just a normal classical random number generated, normal classical algorithms without any focus focus. Yeah. The question is either we can do it. Yes, we can when this is locally, but the question is only in resources. Because you may need huge resources, even for a small quantum system, you may need huge resources. But when your system is distributed in space, for example, one qubit in the Earth, another qubit in the Alpha Centauri, yeah, it may happen that you cannot simulate it in principle without some additional things about some additional hypotheses that special relativity should be violated or something like this. But this is, of course, too much for such theories. So this is a question about realistic theories. Then people asking, so then everything what happens with single qubit, yes, you can simulate this. Qubit is very simple system. You can simulate it classically. And this is just a question what to do it. So the answer on your question, either it's possible to, either it has a classical analog, it's simply the point of, so then depends on your point of view. So, and XYZ gaze, either they have classical analogs. X gate, of course, this is not. Y and Z, they add some phases. Yes, they add some phases, but you never, for example, when you consider it from the point of logic, the point of logic, you are never interested in classical things with such things like phases. Yeah, so from one side, this is you can this classically you have a classical analog. From another side, you in classical picture do not have such notion as a phase. This is the point, because in classical physics you don't ever have also superpositions. But again, still, when you consider a Bloch sphere, when you consider this description, everything can be perfectly simulated with a classical computer. It's not a problem at all. Yeah, so this quantum things appears a little bit later. One more question was about XYZ. I don't remember something. XYZ, either we can do some other gates with XYZ. XYZ gates, when you multiply them, you get XYZ again. So something like this, maybe not. Okay, let's continue. And now I'm going to another part. So what we now understood from classical mechanics. First of all, from quantum mechanics, from quantum physics and quantum information, we understood what is the state of qubit of the elementary quantum system. Yeah, we understood what is unitary evolution, how it involved this state involved in time. And now I would like you to give a little bit more physical insight on this and to explain to you how this is implemented physically. And the next few slides will be maybe one of the most difficult in my lecture from the mathematical point of view. But if you're not a physics student, but please try to understand it. I realize that this is not easy things. Okay, how to describe this unitary operation? Very similar story like in classical mechanics, there is differential equation. And this differential equation is named after Erwin Schrödinger, Professor Erwin Schrödinger, who has invented this. And he has found that psi from t, c depends on time, it should satisfy this equation. So this is first derivative. H with such bar is a Planck constant. I believe everybody knows what is it. And H is a matrix of operator, which calls Hamiltonian, or operator of energy. It's really related to the energy of the system. And this operator should be Hermitian. Again, Hermitian operator. So this means that Hermitian conjugated should be the same operator. Okay, when we want to understand unitary evolution, we should solve this equation. And this equation allows at least a formal solution. And this formal solution results us to a unitary operator, to such unitary operator. This is the case when Hamiltonian does not depend on time. When it depends on time, the story is a little bit more difficult, but this will also be unitary evolution. So this results any unitary operator, you can act by this unitary operator. So you can take this unitary operator, so apply it to initial fiducial vector and get after that solution to the Schrödinger equation. A little bit more formal, how it works in practice. In practice, this works that we can try to find solution of Schrödinger equation in such a form, like a product of such an exponent e in minus EH. After that, some constant, some real constant e. We will specify what means this constant a little bit later, t. And after that, some state which depends on this constant. Okay, what we need to substitute this ansatz here. And this result us to the following equation, which calls stationary Schrödinger equation or stationary state. He is equal E. For the qubit H is the matrix. And you can recognize, if you know linear algebra, you can recognize that this eigenvalues equation. E are eigenstates of Hamiltonian, and this E are eigenvalues of the Hamiltonian. You can solve this equation. In case of qubit, this is an elementary problem. This is just 2 times 2 matrix, eigenvalues and eigen problems of 2 times 2 matrices. You can solve it and get these solutions, which will be stationary solutions. Non-stationary solutions or general solutions will be simply a superposition of such solutions. So I take one solution with one E, put it here with such some constants. This will be still solution. And the sum over all of them will also be solution of all these stationary equation. The question is only to find these constants, and we can find these constants if you study mathematical analysis. You know that we can find it by through the knowledge of initial conditions. So about our fiducial or initial state. Okay, this is how things works. And now let me go to some elementary or even toy example. I understand that physicists can say me now, oh, it's not realistic, and they will be right. But let's consider how things works. And after that, we will discuss critics about this model. This is a toy model. So let's again dimensional double potential well, but this double potential, 2 wells are situated far away from each other, for example. Yes, so this is a space. In this case, and they are not deep enough, they have, again, for the people who understand quantum mechanics, I say that we suppose that only one level can be associated with each well. And in this case, we have very easy Hamilton operator. This is actually proportional to the identity operator, epsilon, some E, large E with I, looking like this. Eigenstates, eigenvalues are very easy to find because you have only one eigenvalues, actually 2 eigenvalues, but they are the same and have the values of epsilon, and 2 eigenstates that we write as 0 and 1. What I would like to do after that, After that, I would like to switch on some interaction. So let's, for example, do these two wells a little bit more close. I understand that this is just a toy things, but just to explain how things are working. Interaction or this closeness means that appears something other. Delta, for example, with sigma x. Sigma x is the same matrix as for x Pauli matrix as for x gate. Your Hamiltonian is now such a matrix. Very easy to find eigenstates and eigenvalues of this matrix. They are written here and here. Eigenstates are like this, 1/2, 0, minus plus 1. But look, now we have not one eigenvalues, but two eigenvalues. Here, epsilon minus, y minus delta and y plus delta. One corresponds to one energy level, another one corresponds to another energy level. And general solution will be a superposition of all these states. So this is some constant C plus. After that, you have this exponent time part of the solution. In this case, y is E plus delta, and here is E plus, and the same story plus E minus. And now you can suppose that your initial state was C from 0. Those of you who was studying differential equation can easily solve it, and to get such a solution. You see that when time is 0, this is exactly what we had. And after that, this means particle was here. After that, we switch on, for example, some interaction, appears two levels, and this evolves like this. So in some moment of time, we have superposition, and you may even fix some time here and to get some gate, some unitary evolution from the 0 to get superposition of 0 and 1. Yeah, interesting story, interesting question. And this is almost all that I would like to tell you about logical operators and evolution and quantum evolution. And what we need more is to understand about measurements. Because you remember that we need, for our theory, for our deep understanding, we need three components. First components, to understand what is states, we understood it. To understand time evolution, we understood it. And to understood with measurements, because this part is just what you can see on the paper or on your monitors. It is not so far related to physics. So in order to relate it to the physics, we need another axioms of quantum mechanics, which related to measurements, because when we make measurements, we can do something. You maybe already know that probability to find, for example, these qubits here or here, so this will be a measurement operators known as a qubit readout. This is absolute module square, yes, modulus absolute squared absolute value of this coefficients. So in this case, this is cosine square on this argument, and this sinus squared on these arguments. And this is the essence of so-called Born rules. But before I go to the Born rules, I should tell you about a bit more math. And now we are going to do with this math. So instead of, maybe you already know that this word cat vectors is just the last three letters in the English word bracket here. And the designation means that there exists something more, bra vectors. And let's try to understand what is it. I will not give you now a really deep mathematical theory, because I understand that this is not the essence of this group, but of this school. But nevertheless, let's try to understand it at least somehow intuitively. So what we have? We have cat vector, This is our designation. So you have it's written like this, psi, and this can be written like a superposition. So with basis vectors C0 0 plus C1 1, or such a vector column C0 C1. Okay, when we have column vector, we may have row vector. And row vector, this is actually what we say as bra vector. But this is not only transposition of this vector. So I have written with another letters, with another coordinates, and this is actually another vectors. But if you transpose this vector, you can get C0 star, C1 star. This is another vector, I think, because for my purposes, I will need another vectors also, some vectors phi, yeah? And this can be written like this. So this is now a row vector. An important thing is that we should transpose it and complex conjugate. This is the definition. And what we need also here, we will write it with like this. This is bra vector, the first three letters from here, yeah? And this is written like this. Okay, any ket vectors, to any ket vectors, you can put into correspondence bra vectors. This is actually almost the same, just a transposition or conjugation operators. Transposition and complex conjugation, nothing more. Yeah, so you have one-to-one correspondence. This is a bit different mathematical object, but actually to each bra ket vector, you may take into correspondence one another bra vector. And of course, two vectors, once they're written like this, for two vectors, you can you can define some operations. A third operation is scalar product. Scalar product phi and psi of two vectors is simply like this, like in geometry. This is just products of two vectors. This vector is multiplied with these vectors. However, this is not all that. So this is a number. The result of scalar product is a number. I would say that scalar product, this is like a machine. At the input of this machine, you get two vectors. And at the output, you get a number. Give me two vectors and obtain two numbers. This is the scalar product. Okay? But this is not only the product that is possible to have here, because there is another kind of product which is called dyadic product, which is written like this. And when you look like this, so you simply multiply this vector in another order, this one and this one, first this and this vector column on the vector row, and you get already matrix or operators, which looks like this. You see its elements C0, D0 star, here C0 still, but D0 1 star, and the row C1, D0 star, C1, D1, 0 star. You can act by this vector on another vector and again vector again. So this is an operator or matrix, two-dimensional matrix. This is an important part of the story. So let's try. There is one question, maybe it's time to answer. Is the bra vector of an observable? No, this is not an observable. Bra vector cannot be considered as an observable. The bra vector is simply another designation of a state. So you can describe your state either by ket vectors or by bra vector, but this is not observable. About observable, we will talk a little bit later. This is not observable. This is just math needed to observation. Okay, when we have such operators, I would like now to present you some more important examples, of these dyadic products. It calls projection operators. Projection on zero. Such an operator, P0, 0, 0, and this is such matrix. So you see that by acting on some vectors, this takes only its first components, or in this notation, 0 components maybe. projection of 1 on 1. It looks like this operator. And this is still almost all 0, but only one here you have 1. So this is a projection like in geometry. And if you consider, just an example, if you consider your state, which looking like this, let's apply one projection operator, just a moment, projection operator P0 to this state, you get again a state cosinus theta over 2 by 0. So projection operator like this is applied to this vector, you get a new vector. But this vector is not normalized. So this is not on the block sphere. Yeah. So in order to make it physical, you should it additionally normalized. And the same story can be seen here. P1 applied to this vector, you get only this part of this vector, and again, vector is not normalized. So to make it physical, you should renormalize it. Actually, in physics, we say that state is presented not by vectors, but so-called rays of vectors. Rays of vectors, this is all vectors which can be normalized to one vectors. Yeah. But okay, this simply means that when you get, as a result of linear operations, some new vector, in order to make it physical, you should renormalize it. And it's a really fantastic situation, but this operation can be implemented physically. They can be implemented physically, but only with random results. Either this, either this. When you make some procedure, and we will call about this procedure, which calls quantum state reduction or measurement, you in principle have a possibility to realize such operation, but you do not know your result, because you will get either this or this. Okay. And another important story about projection operator is that such relation, that square of projection operator is again a projection operator. This is an important thing. This is an important story. Yeah. Okay, maybe before go further, I will go to answer some questions. So, observable.
There are no questions so far, only comments.
Observable quantities in quantum mechanics are matrix element of some. This we will talk about this. Yeah, we will talk about this, Mikita, but not right now, or a little bit later. Okay, because observable quantities, what's observable quantities, and now we are ready to formulate these rules for measurement. This will be another axiomatic. So we have quantum physics, quantum mechanics. It's not only Schrödinger equation. It's not only time evolution. This is not so. We have formulated again what is state, what is time evolution, and now we have short axiomatic. What is measurement? What we obtain as a measurement outcome. And this rule was formulated by Max Born. He told the following things. Here, this is in application to the qubit. But of course, you understand that this is more general rule, which can be applied to anything else. If you want to measure something, let's say about a qubit. If you want to make qubit readout, you will get either 0, either 1 results with probability Pn, which for each quantum state, pure quantum state, theta phi, I will mark now quantum states by theta and phi, because they depend on two numbers, like this. So you have such a, yes, this is a kind of matrix element. Here is in the middle projection operator Pn, and this is simply in these brackets around this, so these numbers. This is axiom, well-known axiom that has the same maybe importance as Schrödinger equation itself. Quantum mechanics does not work without this. In order to formulate quantum mechanics, you need quantum, not only Schrödinger equation, you need to connect your state with the result which you have in the lab. In the lab, you have almost always, yes, for almost always situation, you have a statistical result, stochastic result. Probability to get these outcomes is given by such a rule. So this is a fundamental thing which is of fundamental importance in quantum physics. You can write it down in a little bit more not so complicated form, but also used in textbooks on quantum mechanics. You can write down what is your projection operator to remember that this is projection on, for example, on the state n. And in this case, P0 is a squared absolute value of such things, theta phi 0, and P1 is a squared absolute value of this scalar product, theta phi and 1. You can revert it, of course. Not only here, bra vectors, you see that I have written state here and this here. You can revert. Maybe more pedagogically correct it would be to revert it, but nevertheless, this is the same. This is still correct relation. So I mean 0 theta phi instead of theta phi 0, but nevertheless, it doesn't play any role. Okay, let's continue. Let's continue the mod, and like I tell you, that projection operator can be realized in the lab. And this is actually what do some measurements, not all measurements, but so-called non-demolition measurements. When non-demolition measurements means that when you get the value of qubit, for example, 0, yeah, this is your state is in the state 0. When you get the value 1, your state, your qubit will be, your system after this measurement will be 1. Formally, this is written like this: the projection operator applied to the state, but this should be also normalized. Please do not consider this normalization as this is a kind of nonlinear operation. Not. This is not nonlinear operation, since in principle, in quantum mechanics, we consider all quantum states with respect to normalization. So this is just a formal thing that you should understand. So that you should clarify it. So sometimes, as a result of measurements for a very special class of measurement, which calls non-demolition measurements, we can realize this operation. And psi n will be as an ended case, but unfortunately, this is not for any measurements. This is just a class of measurements. Usually, when you apply some measurements, this calls totally even destroy your qubit, or when this is optical implementation, for example, or may happen other not so nice things. Okay, and now I will talk a bit about physical implementation on example of single polarized photons. Qubit, because I'm an optician, I'm doing my quantum research with quantum optics. This is very natural for me to talk about optical implementation of these measurements with qubits. So how we can implement qubit readout? Maybe you know, maybe not, that electromagnetic field can be polarized. This means that electric field may be directed, this is oscillated, but this is directed in, for example, one direction, for example, in vertical direction, or in horizontal direction. This property is called electromagnetic field. Quantum particle which corresponds to electromagnetic field is called photons. Photon. And photon itself can be polarized. It may have different polarization, horizontal, vertical. This means electric field, which has the direction of the electric field of electric field associated with this photon, horizontal, vertical, or something intermediate, even some complex superposition of this vector, so rotational, some polarization, whatever you want. And of course, we can prepare this photon with some polarization in some quantum state, which will be characterized by polarization angles, theta and phi. And now I would like to understand how this works. This device, which calls polarization analyzer, has several parts. First part is so-called polarization beam splitter. What is it? With this device, for example, horizontally polarized photon is always transmitted, and it is never transmitted, it is never reflected. So when your photon is horizontally polarized, this will be transmitted. And after that, here will be the photodetector, which can absorb these photons and demonstrate us the result. When your photon is vertically polarized, this will be reflected and absorbed by these detectors, and detectors will click. And you understand that your photon was in vertical polarization, for example. But what happens when your photon is not in horizontal, neither in vertical polarization, when this is something intermediate? In this case, you will get randomly here result or here result. This is, by the way, how some quantum number generators works, and some commercially available quantum number generators. This is not a pseudo number, random numbers. This is true quantum process, because nobody can in principle predict what happens here. We do not understand how this works. And it seems that we cannot understand it even. Because what happens at the end, which detectors will be clicked, this one or this one, depends only on the random case, on what happens. And okay, but what can be? This is how the work when the all work idealized. And now I will start to tell you about one problem. That means researcher who is doing with, or engineers who are doing with quantum computers, actually they have a lot of problems, and this is not the most important, but nevertheless this always exists. And what these problems means? Just imagine that photon was here already, and maybe it was even absorbed by these detectors, but detectors in some reason didn't click. For example, it was reflected or something like this, it's happened. Okay, this is not the most important problem, because in this case we can say, okay, we can not consider this event at all. But instead of this, from universe, from some, I don't know, cosmic radiation may come another photon, and these detectors comes, also due to small radioactivity in the detectors. So photons was here, but you get this click. This means that you have measurement with errors. And how to describe it? In this case, similar to classical situation, we should write P, that conditional probability to get the click K, for example, the event 1 under K, given that the real value was N. Photon was here, but with some probability you get here. And of course, when this is here, so this is here. So you have again something like a response function, classical response function. But in this case, we should modify it. This means our quantum rule. Our probability, pk, to get this click will now be given by such a formula, law of total probability. This conditional probability k to get the number k under conditions that this number happens. And here is true Born rule for perfect measurements. Theta phi, Pn, projection operator, theta phi. What we can do not know the following. We can put this sum with this number inside this scalar product. And you can see that this is now a new operator, some operator. This operator is called positive operator valued measure, known by abbreviation POVM. And the Born rule in this case looks like this, that this is now theta phi, and theta phi is scalar product, but inside is not a projection operator, but the POVM operator. POVM, positive operator valued measure, this is a set of operators which describe your measurement. In principle, there are some axiomatics which this operator should satisfy. So I can tell that this should be normalized set of operators and they should be so-called positive definite. When this satisfied to such condition, this and you have found this theoretically, so this means that this exists, this can be implemented experimentally. But this is not the essence of this lecture. But what you should understand that in the most general form, the word is imperfect, and imperfection from measurements are sometimes important. When another important issue is imperfection from states, but this will be considered a bit later. Okay, let's do some summary. Yeah, for this part of the lecture, what we have studied. First of all, you should understand what is pure state in for one qubit. This is vectors psi in a Hilbert space of states. This is not real physical states, not real our configurational space in which we work. This is some space of states, Hilbert space of states. This is an important issue, and this is an issue which for which we have a very big difference between classical and quantum mechanics. So vector psi are quite so this states, quantum states are different in quantum and classical domains. Yeah, so states, states, classical states, this is numbers, here's are vectors. Measurements in quantum mechanics are given by Born rules, by Born's rule, which looks like this. This is also a fundamental issue. And time evolution, that is quantum logical gates. You can consider it's how it is implemented with Schrödinger equation, but this I only gave you as an example. Nevertheless, you can always put so, never try to do like this, because this is just a random combination of some operations, yeah, just for demonstration. But nevertheless, time evolution in quantum mechanics is also described by Schrödinger equation. And for us, this is important that this is quantum gates. So, three things again. Pure states are vectors. Measurements are given by Born rule. Time evolution, this is Schrödinger equation. And its particular solutions are leads us to quantum logical gates. So this is the end of this part of my lecture about qubit, and maybe I will answer some questions. From DTP Kulinsky question: do we need counterintuitive ket-bra vectors and Hilbert space at all? They are unobservable. It seems that all need is just matrices. How to tell you? If you have just matrices, then please explain me how to describe this rule. Actually, state, and this will be can also be described by a matrix. I agree. State can be described by a matrix. But okay, when you describe it, this is I will tell you by projection operator. This is will be the essence of my last lecture. But nevertheless, you always need to describe quantum states. For pure quantum state, natural description is cat and bra vectors, because having only matrices, you can not understand what do you measure. Measurement results, these measurement results depends on two things. What do you measure, which describe your observables or your POVM, what you can observe. And this is described by your state, that's the vectors. So in this relation, you need, but you may be right in another situation, because quantum mechanics is a science of representations. And actually, you can describe all quantum mechanics in another representation where no cat and bra vectors exist. And such representations, for example, there exists phase space representation of quantum mechanics. You will have totally classical descriptions that I described to you before, but with some very interesting exceptions. This exception means that for probability distributions, in this case, you may have formally negative values, so negative probabilities. These negative probabilities are assigned to states, but not to experimental results, because in experiments, you never have, of course, negative probabilities. So you may describe quantum mechanics in such a way, it's not a problem. When this is more close to your intuitive, you're welcome to phase-space representation of quantum mechanics. These matrices here, but this is not the essence of our school. So, other questions? I do not see. Okay, and now I will continue with another lecture. Just a moment. This is another part of my lecture. So it seems that I do my lecture. So when something is still so, because we have a time, so I believe we can still have some time for questions. So please don't hesitate to ask questions, because we really have time. Okay. Another part of my lecture, multi-qubit systems. And now we are going from one qubit to many qubits. And this is actually what happened with quantum computers. And okay, let's continue what happens here. In classical domain, in classical information, when you have n-bit system or n-bit states, they can be each, they have 2 in n possible, there is 2 in n possible combinations for them. So for n bits, there is 2 in n possible states. We are writing them like this. 0, 0, 0, for example, this index which designate each classical bits here and here. And now is very important property of quantum system, because it turns out that quantum systems work like this, that our n-qubit system will have 2 in n basis vectors, which we write either like this with this strange sign of multiplication, of outer multiplication. This is quite important things, because think about, there are a lot of, in physics, there are a lot of physical systems which are described by linear equations. But it seems only quantum systems during scaling so may result in such increasing of their Hilbert spaces. This is really interesting situation. And this means that our basis now contains 2 in n vectors. This is the answer on some question, by the way. But here we also have 2 in n combination. What this means? This means that any pure state can now be written like this: k from 1, or as a combination of all these basis vectors. K from 1 to 2 in n, ck, k, where k is, for example, a binary. So this is k1, k2, kn, but in a binary base, because this is 0 and 1. Each k is 0 or 1, 0 or 1. So you can associate it with some numbers in the binary base, and you can say that this is your number. Look what happens when n is, for example, when we have one not really large quantum system, but which includes, for example, 300 qubits. 2 in 300 is a really huge number. This is actually more than the number of elementary particles in the universe, it seems, or at least atoms in the universe. And when you want to model this quantum system, this small quantum system with 3 qubits, this is not really large, in a classical computer, you need a memory register in order to write there 2 in n, okay, 2 in n minus 1, because normalization condition, yeah, even not 1, but okay, 2 in n approximately, complex numbers. So your classical computer should have a size like the whole universe. Of course, this is impossible, even to imagine. Yeah. And but what you can do when you want to describe this quantum system, and this is your molecule or something like this, you can build another quantum system which you can which is described by the same Hamiltonian, and to which you have a good control, and simply to give them alone to evolve it. And this is actually what happens when we make quantum simulations. Yeah. So this is an example already of a quantum algorithm, quantum simulation. Okay, for us, this is now important that the new basis is built like this. And here we are going to an important notion in quantum computing, not only in quantum computing, but in the whole quantum information science, which is called 2-qubit entanglement, or simply entangled states. This really fundamental notion, entanglement, no entanglement for classical system, and we even do not have an analogy of entanglement in classical domain. Yeah, and what I will tell about this is entanglement of pure states, and this is also an important, but please note that this science is now very well developed, and when you want to understand more about it, I recommend you this reference. In this paper you can read, this is a review paper in the Review of Modern Physics for 2009 by the family of Gorodetsky from Gdansk, Poland. And this is a very good paper where you can read almost all to this time, 2009, which was known about quantum entanglement. So I really recommend you this paper. Okay, among a lot of states, 2-qubit states, let's say now about 2-qubit states, there are such states which are entangled, and there are such states which are not entangled. And it is easier to define what are unentangled states or separable states. So, Volodymyr, I believe we can do some pauses, because it's in schedule, or it can take 10 minutes more.
Yes, it would be nice to make a small coffee break now.
Yeah,
like
let's do
10 minutes.
Break. Yeah,
10 minutes and then continue.
Yeah, and we will continue in 10 minutes. If you have any question, you can now ask during coffee break. So we have one question because coffee break, but I believe I can answer. Why does the space of states of qubit is only two-dimensional in contrary to different another quantum mechanical system like hydrogen upper with dimension is countable infinite or even continuous, which is more natural for a complicated system, in my opinion. I mean, where can we find such a simple system which may be just a moment, which may be described with only two dimensions, maybe an operation of particle spin. Yeah, very good question. This is actually what I do in research, and this is actually what I always say to other people. Continuous variable system or system with infinite Hilbert space. Of course, this is more natural. For example, a mode of electromagnetic field. This is a mode of harmonic oscillator. Okay, and this infinite dimensional Hilbert space, we meet it very oftenly. In order to do two-dimensional system from electromagnetic field, we should first say that we have only one photon. So for this case, we should make only single photon state, so restriction already of the Hilbert space, and with polarization or with another degree of freedom, it's always possible. There are, of course, a number of now systems which people working to implement qubits. For example, Josephson junctions. Yeah, very now famous things. This is based on superconduction. Yeah, spin of electron is a two-dimensional system. It's also such a like a qubit. Yeah. And some in atoms, when you have, so now you can isolate your atom in some trap, and you can do these atoms with electrons, with levels of electrons, and two of them will be quite good. Between two of them, you can quite good operate, and this also is a qubit. Atomic nuclei, they also can be considered as a qubit. In principle, there are now a huge number of different systems which can be done as a qubit. Sometimes this is done really artificially because your dimension of your Hilbert space is much more than two. For example, this is why such people like me don't want to do with qubits. We are doing with other systems. And we try to use the whole this power of this infinite dimensional Hilbert space. Sometimes it works, sometimes not, but nevertheless, there is also an important direction in this research. Actually, all quantum information can be subdivided into this research area, can be subdivided in two big fields: continuous variable and discrete variable. What I'm talking about you now is a discrete variable, but my field of research actually is a continuous variable quantum information. So this for infinite dimensional Hilbert spaces. Of course, I think that this is also interesting and maybe even more interesting than qubits, but this is because this is my field of research, I understand. Can you please explain a bit more in what sense atomic nuclei can be understood as a qubit? Nice things. For example, atomic, when this nuclei have a spin, and this spin is a very rare situation, but it can be this is 1/2, so spin up and spin down can be considered as a qubit because you see that spin is described by Pauli matrices also. And you can consider this spin when you have an access to operate with this spin, when you have an access to make measurements and to make to realize quantum logic. So you can try to do it. And by the way, this is done. But sometimes, very, very often, atomic nuclei have not such spin as 1/2, 1/2. They have another spins, and this is the problem. And in this case, you can, for example, somehow restrict again your Hilbert space with some methods. but any particles with spin R1/2 in principle are natural candidates for qubits. Of course, with electrons is difficult to do, but when you have some electrons, for example, very interesting thing, this is so-called nitrogen vacations. This is when you have in diamonds, when you have a crystal of diamond and one atom is replaced, one of the carbon atom is replaced with nitrogen. So another carbon atom disappears, and this will be such a very interesting system of nitrogen and vacation inside a diamond crystal. And it has a very nice electronic configuration. It can be implemented to qubit there with a good control, with a good also things. And what is also interesting is that by controlling electrons, you may also control some nuclei inside, it seems, nitrogen atom, if I'm not wrong. This is the case, but also in molecules, the nuclei are usually this nuclei is very interesting because nuclei are usually very good isolated. And this is actually what we need for quantum system. This is what I will talk tomorrow.
I would like to add something that on Thursday we will have like a lecture about the construction of some spin systems and how classical machine learning can also help with developing the good qubit candidates, and another two-level system, and the centers will be also discussed there.
Perfect. Then welcome on Thursday, lecture on Thursday. Thank you very much. A question about details of spin system I will address to other lectures. So my profession, sorry, is so there are some questions. How do we measure? So I'm doing almost with optical fields. You may ask me about optical measurements. Yes, of course, I can also answer you about spins, but I believe on Thursday you will answer your question. How to implement these measurements procedures. So, Vladimir, I believe we can continue since we had a coffee break at 1.
Yeah, it was a short coffee break. Anyway, yeah, we can continue. This will be the last section of today's day, like the last part of lecture. And I believe you want to finish at 16:40, so 20.
Well, let's see. Maybe right? Maybe I will believe even earlier, but the most because I do not want to start today with new lectures for tomorrow. But we spoke part of my lecture. Okay, ladies and gentlemen, let's continue. And now we will continue with entanglement. What is this mysterious property of quantum system? So how to define what is entangled states? Actually, for me, it's easier to define what is unentangled state or separable state. Separable states or unentangled states is such a state C capital, that there exists two other states, phi1 and phi2, that it can be presented like this. Actually, all other states are entangled. And this is the definition. So when you cannot present your two-qubit or two-partite in general, it's not only for qubit, two-partite system in such a form, so then your state is entangled. And sometimes it is not clear what is entangled, what is unentangled. Because, for example, we have such a situation. This is not like this. Yeah, so this is not separable. But when we look at this more attentively, we can use school algebra and to write it like this. So we have found two states and understand that this is now separable, which presented in such a form, because this is now as phi1 and this is now as phi2. This is a separable state. But look what happened if I change here one phase here. This was plus, and now I made minus. It's already impossible to present in such a form. And this state is entangled. Entanglement is really a miracle property. It's you can read a lot about this property in this review paper if you're interested in. And this is what we start to understand from the famous work of Einstein, Podolsky, and Rosen. This is clearly related to Bell non-locality and for what we had a last Nobel Prize in physics and so on and so on. This is also a key resource in quantum computation. So for quantum computation, it is important to have entangled states. Why? Once state is separable, you can simulate each qubit separately. And this is already can be done with classical machine. When this is inseparable, you should manipulate with all qubits together and you cannot simulate each qubit separately. This is an important thing. Yeah. Okay. Entanglement is a kind of quantum correlation, class of quantum correlation, but what I would like now to you demonstrate is how to get some entangled states. And for this case, we will study evolution for multi-qubit states or evolution for logical gates. And maybe the most famous logical gate is so-called C-NOT gate, all controlled NOT gate. This is, I mean, from two qubit gates. Okay, what is it and how it works? Look here, this is actually some extension of a classical logic. We have two qubits. One of them we call control qubits, which we use as for controlling, and another is a target qubit. When your qubit, control qubit is in a state 0, then nothing happens with your target qubit. But if you want to change your target qubit, you should put here on the control qubit 1, and nothing will be changed here. But for target qubit, this will be n, and this signs plus in circle means sum in modulo 2. That means that this is totally opposite. When it was 0, this is 1. When this was 1, this is 0. So C-NOT gate is simply change your qubit state if the control, the state of your target qubit, if the control qubit is in the state 1. Of course, for when we consider classical unitary transformation, this will be even more rich structure. Nevertheless, let's see how it looks in the question or in the matrix designation. So U C naught, you can write like this. So this, I just remember how it's written, basis. Basis, just let me show again, sorry, to my first slide. That basis, when you look at these vectors, they are usually written, some authors use another order, but I prefer to use this one, like numbers in a binary system. So the first was all zeros, after that 1, and so on. So this is, we simply use like numbers in the binary systems, yeah? And the matrix of C0 gates look like this, so it makes nothing with first qubit, and reverse the second qubit when the first qubit in the state 1. So this exactly described by this matrix. Okay, very nice. Let's continue, and let's now to combine this C0 gate with another gate, with Hadamard gate. So first we put on this qubit Hadamard gate, and after that we put here controlled gate. So again, I would like to show you, maybe I didn't say, because other colleagues told me that I should maybe bring your attention to the thing that this is how C0 gate is written in quantum circuits. There's already 2 lines. Each line is called a quantum wire. Please do not consider that this is really real physical wire. This is simply a unitary evolution, yeah, for each qubit. And here we have such a, maybe such a picture or such a designation for this control, for this C0 gate. So this is for control qubit, and this is for target qubit. For target qubit, this is the same as for NOT gate. Yeah, but this is very clear because NOT gate is exactly making like this. This is from n makes n plus 1. Okay, now we consider that we have, for example, such a simple scheme. First, we have in the first qubit Hadamard gate. And this makes already a superposition. And after that, we have a C0 gate. Let's see what happens. In order to describe it properly, how to describe it, I invite you to the lecture of my colleague, Danila Yakimenko, tomorrow. He will tell a lot about this matrix algebra, how to construct the whole unitary operation for such quantum circuits. But I only want to tell you the next things. First, you have Hadamard gate. Another gate is empty. This means that you should put, this is 2-dimensional Hilbert space. Here we have 4-dimensional Hilbert space. Another qubit is, for another qubit, we do nothing. And this means that we should write an operation which a direct matrix product. Tomorrow, Danila Yakimenko explain you what this means from H Hadamard gate matrix with identity matrix. And tensor product, this is tensor product H and E2. And after that, you apply this C0 gate. So first, let me not to explain you like how this works. This is actually, you can look in internet, and it's not a really difficult story. This is simply each element of this matrix should be multiplied with this matrix. And this means that you will get at the end from 2 matrix 2 times 2, 1 matrix 4 times 4. And this is already a matrix 4 times 4. So their products gives you actually such matrix. This is a matrix, this is a unitary matrix which corresponds to such a scheme. Okay, nice. And let's now consider what happened if I apply to this scheme some inputs. Yeah, for example, if I put 2 qubits here, 2 bits, 2 qubits, 1 qubit in 0 state and another qubit in 0 state to such a scheme, I will get very remarkable quantum entangled state, which calls Bell state. this written like here, it's very easy to understand why it happens actually. Look here, 0, 0, yes, 0, 0, this means that in this row will be only the first vector will be 1 and all other will be 0. So we multiply it and get this, and this corresponds to this superposition. 0, 0 plus 1, 1. This is the first state, which he calls as a Bell state. But this is not only the single one. Another state is very interesting, is called psi plus. When we apply here 0 and 1, again, you can do an exercise. 0, 1, yeah? For 0 and 1, you have here vector 0, 1, 0, 0. You multiply it, get this one, and this is exactly what we get. So instead of 0, 0, 1, 1, we have 1, 0, 1, 1, 0. The states are known as maximally entangled states in some states. Okay. Apply 1 here, the state 1, and here 0. And you apply another Bell states, phi minus, which is almost the same like this, but with sign minus here. And when two qubits in the state 1 here and here, you apply it for such states and get such a result. Another Bell state. So 4 Bell states. Bell states are really important things. They play an extremely important role in quantum information, yes, in quantum information science. And actually, I can tell even more about them, but we can consider only some application. So this is actually the states was used in these experiments on Bell non-locality, which was which was the essence of the last Nobel Prize in 2022. This is exactly what people do, but after that they have made some measurements, and they measurements results to some remarkable results. Okay, we will not speak about this today, but we will play around with these states. Let's consider some toy examples, and we will try to understand something more about these states. For example, we have states, such states, phi plus minus, with 2 states, which is here 0, 0 and 1, 1. And what I would like to do now, I would like to do the following. I will measure the first qubit. I will make qubit readout with the first qubit. With such a sign, we usually mark measurement device which make qubit readout. And you know that the qubit readout is a probabilistic thing. So you can get as a result or 0, either 0 or 1. Yeah, and this is the number n here. But when you have here as the input one of the states, you will always have here, this will be a projection. You get already this. This will be action of projection operator. The state will be reduced. We will be reduction of quantum states. We will talk about this tomorrow, a little bit more details in my lecture tomorrow. And this is like an action of projection operator. So when here is n, you get here the state n. Almost the same as this number. So when you get here 0, this will be 0. When you get here 1, this will be 1. And let's play a little bit more. So this is, let's add here some more things. And this is already an interesting story, which is about quantum classical hybrid schemes. What I mean, that all like this, but I add these things, this guy. this guy is called actually classical wire. So when this is a quantum wire, this is a classical wire. What this makes? This get result n, put it here, and here I realize the gate x in n. When n is 0, this is identity gate. When n is 1, this is x gate. So I can simply switch it depending on the classical information I get here. Look here, with such wires, we have quantum information. With this wire, we have already quantum information. And new things for you that this is a measurement device. Okay, what this means? When we have here, for example, result 0, we put this means that here is also 0. We put this 0 here. This will be identity operator, this will be 0. And of course, if you measure something here, you will get always 0. When you have here result 1, you put it here, the gate xn changed your result, and again, it was here 0, but 1, but this is again 0. Such a stupid scheme, which always gives you 0, but this can be a little bit modified, and with some modification, you can get, for example, such measurements like is done in Bell experiments, but okay, I do not stop on these things. Okay, let's now play with another Bell states, with psi states, 0 and 1. And here we have totally different situation. So when you have psi state here, when this measure 1, this will be always 0. Oh, here is again mistake. This should be plus, sorry. And so this should be plus, but not multiplication. So the sum in modulo 2. So when you have here 0, you always have this 1. And when you have here 1, you have 0 because you have a projection. Here is 0, you have 1. Here is 1, you have 0. And by adding such a classical part with a gate xn, you can get at the output always the state of the qubit, of the second qubit, the state 1. Okay, very simple devices, but they demonstrate you how usually works this projection. That when we measure something and we get a result 0, for example, here, you will always have 0. When this is 1, you have 1. And the same story, but in another direction, it works here. When it's 0, this is 1. When this is 1, this is 0. Okay, now I'm finishing with my this part of my lecture. And for summary, that what we should now understand and what we should study from this part of my lecture. First of all, the basis of multi-qubit states. Yes, this is 2 in n vectors. Actually, a huge numbers of vectors. Yeah, in order to quote arbitrary state, you need 2 in n complex numbers. The next story, entangled and separable states. The definition, I believe you already studied. And what you also need is Bell states. The Bell states here are defined like this. This is an important example of entangled states. I believe you will meet this in other lectures. And also, I have presented you controlled node or C-node gate. More about multi-qubit gates will be on the lecture by my colleague, Dr. Danila Yakimenko, tomorrow after lunch. My task was just introduce you some elementary results. So, Volodymyr, this is all that I planned for today, actually saying. I do not want to split my lecture and not to present another part of the lecture with mixed states and with a number of different states, because just I will announce just what happens tomorrow. Tomorrow I will talk about mixed quantum states, because quantum states cannot be not only pure, but also mixed. And actually, this is what may kill all this idea of quantum computers. Yeah, so this very important things, how environment acts on our quantum systems. And of course, I will not tell you about everything that happens in this domain, but at least I will present you some alternative description of quantum states in terms of density operators. And we will consider one very interesting quantum paradox that sometimes people call as informational paradox. And after that, we will study, understand that I will answer the question that people were asking me about qubit state, that qubit state is a state of, on the sphere of, on the block, is a point of the block sphere, but there are more general states, and even qubit states can be a state inside block sphere. So all this will be tomorrow, and now I believe that I should stop, and I'm ready to answer some questions.
Okay, let's see if there are questions.
I believe, I hope it was, Zari, do we have?
I just wanted to suggest if you want to ask question vocally, you can raise your hand and we will give you a right to speak and ask and have some sort of discussion maybe.
I hope my lectures were not so difficult that people understood nothing, and now they can't don't know what to ask. This is quantum science. Sorry, I understand. This is not easy.
I think it was good. You gave a very nice basics, even for those who are not, who have no experience in theoretical physics. So I think it should be fine. Also, like answering the question that someone asked before about 128 bits, what is the same number in qubits? I think like this slide answers it.
Mikita, is it correct that signals are propagating along quantum wires? Mikita, you should understand what means quantum wires is a very big abstraction. In quantum computers, you have no wires at all. So you may have no wires, yeah? Because quantum wire is just a unitary evolution. You should not consider it as a physical wire where you have some propagation. Sometimes this is true. Sometimes it's true, for example, for optical qubits. In this case, optical qubits, so this is separate photons, may distribute in the space between these gates, which are implemented by optical elements. And this is true in this case, but this is not the case for all this for all sedation, because this can be simply a time evolution with a qubit system. So this, please do not consider wires so this is this is quartic wires. So this is not real wires. Yeah, that it's only in some physical implementations they are looking like wires. But this is not the case in general. Yeah. Volodymyr, I cannot
yes,
hear.
Alexandra has another question. I'll unmute her now.
Yes, thank you. Can you show the slide where there was a like product of Hadamard operator and the E2 matrix?
I believe you mean this one, yeah?
Yeah, yes. And after this, you had the slides where we have like state, yes, 0, 0, and
yeah.
different. How, if we have some distinct matrix here at the red, but how we, at the next, when we have some 0, 0, and we have there not this matrix, but the linear combination of 0, 0, 1, 1, for example. Why is it happening?
Okay, I understood you. So how to get the states? First of all, you should consider that here we have some, so I made some simplifications, and I don't like to do like this, but sometimes people are doing like this. So you should not write this. There are some abstraction, operator and matrices. Yeah, operator is some abstract object, but it's not a matrix. So here we have, should we apply? We should not apply it to a vector at all, yeah? We should apply it to vector representation of the state. And vector representation of the state should be considered in such an ordered basis, but only for 2 qubits, okay? This means, for example, for this case, what this means, that this vector, this is column vector, it has such a coordinates 1, 0, 0, and 0. If you see do you see my mouse now?
Yes, yes.
So 1, I can try to annotate, but sorry, this mouse, it will be really stupidly seen. Oh, something like this. Okay, so this is 1. One of my PhD students can write perfectly with mouse. I cannot, unfortunately. Oh, almost perfect. Look here. So this actually what we have like state, like this state. Okay, and when you multiply this matrix with this vector, this matrix with this vector, you will get result that your vector will be 1 over 2. Oh, I'm almost expert now with writing by mouse. And here is 1, 0, 0, 1. Actually, this is this state, because your basis is, I remember, is 0, 0, first basis element, another basis is 0, 1. After that, you have 0, 1, 0, and here you have 0, 0. Oh, something like this. So this is this vector. So do I answer your question? So, okay, thank you very much. This was my aim to make things clear, maybe very easy, and sometimes this is very simplified, but you should be prepared for the next lectures, because quantum machine learning, this will not be quantum computing, but also quantum machine learning.
Any more questions from the audience? Again, if you want to ask it like with your voice, you can just raise the hand and I will give you the possibility to talk. Mikhailo is asking how long were you studying the quantum physics topics?
Wow, Mikhailo, from 1992, when I was first made my bachelor work, and up to today. You can calculate how long it. More than 30 years. And still I cannot say that I know everything. Only some small things.
Please, Stanislav.
Hello. I would like to ask the question. Sorry.
I cannot hear.
Did Stanislav wanted to ask something or not? Try again.
Can you hear me?
Yes.
Yeah, okay, perfect. I would like to ask about the physical representation, about the physical meaning of different quantum gates. So in different representation of qubits, it's like photon or maybe qubit could be any two-level system, if I understand it right.
Two levels, yeah.
Two-level system, yeah.
There is in principle some criteria which should qubits satisfy, which physical system should satisfy in order it would be good qubits. This is not the Vincenzo criteria so-called. This is not simply two-qubit system, because you should good control to have some measurements, some implementation of another systems and so on.
Okay, and in different representations of qubits, how we can understand the quantum gates, for example, CNOT gate, how they are can be realized? I don't know.
How they can be implemented in other systems? Yeah.
Yes. Yes.
Oh, this is a very good question. I believe somebody will tell you. So I'm not really an expert how it's done. For example, with Josephson junction, with other systems like atomic systems. So then in atomic systems, so what you need a control of your system, and depending on what you can implement, so depends your physical realization. In optics, this is actually quite easy task. Also, there are different optical realization. In optics, you have just optical elements. It turns out that if you have, if you can create single photons, so such gates, any such gates you can also create. So such gates, as I read, so for example, NMR gate at least can be done, and a lot of other gates are feasible to do. In other systems, for example, when this is an atom in some traps, you need to implement some control for their system, and this control you can do via electromagnetic interaction, for example, with lasers, yeah, and you can do it after that. So this is you may implement some very special laser pulses which make you exactly such operations on your qubits. Of course, this is not a very easy task. How to implement in superconducting qubits, to be honest, have no idea, or I have, but not so deep as I can discuss it here, but it's also always realized. And nevertheless, in many situations of atomic fields, this is controlling through laser fields, with help of laser fields. But it's not so easy to do. This is very difficult engineering task. What books, Ukrainian and or English, would you recommend to read? You're welcome, Stanislav. Recommend to read to better acknowledging quantum physics, and send the article. Oh, books there are. So it depends on what you want to study, actually, saying. In quantum information, in the field of quantum information, there is well-known books which calls, oh, I can maybe, no, my camera doesn't work now properly. Oh, sorry. Recommend you, there is a book, Nielsen Chuang, Quantum Computation and Quantum Information. Maybe I will write the first author in the Nielsen. And my also in chat. Sorry. Nielsen. So this is first authors, and this is you can simply Google and find this book in English. This is a perfect book, perfect introduction to what I told today. But actually, quantum science is now all this quantum story. Quantum science is, we have a very big community with very different topics of research. Not only quantum computers, but also quantum communication, quantum metrology, fundamental research, for example. I'm personally working in the field of quantum optics. In the field of quantum optics, we have our own books that if you're interested can also see. Yes, exactly. This is here is written, Isaac Schack and Michael Nielsen. Yeah. And I can recommend you many other books that if you would tell me exactly which field of research you're interested in. And are there any advanced mathematical subjects that are used in modern quantum computing information research? I'm starting my master in math, and here would like to know that topic focus if I want. Yeah, of course. So, for example, in this area, so as you see, you need linear algebra and probability theory. But of course, this is not the case. So in quantum optics, we use, for example, very actively phase space representation. For these purpose, you should know functional analysis. So distribution theory, for example, you should, this is closely related to the group theory and even to such area as a quantum group theory, but not really directly related. So this is not necessary to study this topic of research, but group theory you need for sure for this. And of course, differential equations. Yes, this is because without this, it doesn't work. And maybe some advances in formal algebra, since contemporary quantum systems are very difficult to describe. And when you start to understand what's a relation with mathematical objects, it appears to be very interesting. Also, a lot of, but this is only if you consider it from the physical point of view. If you consider it from the mathematical point of view, a lot of relations also to the number theory, a lot of relations to other mathematical things which are used in cryptography. For example, now very popular is so-called post-quantum cryptography. This is not really quantum science, but simply people trying to do such algorithms which are stable against attack with quantum computers. But this should be a quantum algorithm. So you may also consider such situations. So depending, again, quantum field of research is now very, very wide in the world. So we have not only one community, in our community, we have a lot of sub-communities. So this is, everything depends on what you are interested in. So if you are really interested, if you are a Ukrainian student, if you are interested, you can also consider to study what happens in Kyiv Academic University. We have master program, as I said, for quantum research. And this can be, by the way, a good opportunity to you at least to orient in which field you want to study in or to make research in the future.